All right, Alan, I got to tell you some news. I was floating through LinkedIn today. Fabric Air bought Borealis Wind. Borealis Wind's been acquired.
Get out.
I'm telling you, and you know what makes me, I'm super happy for Borealis Wind. But Daniela Roper, if you're listening, why we didn't get the exclusive to let this out, we don't know. Where's the love?
Where is the love? Exactly.
So we're going to jump into some things this week. Maybe talk about this Fabric Air and Borealis tie-up here later on. But what we're going to discuss now is Equinor actually pausing an offshore floating wind farm, just kind of based on basically commercial right now is what it looks like. The technical side and the commercial side not lining up to be the project they want right now. And then also just a quick segment on EROV for wind turbine services. So a project that Fugro is involved with and some other government agencies to basically electrify and autonomize some of the offshore wind farm maintenance activities in the North Sea.
And then we take a look at the recent publication from DNV on the challenges of wind turbine blade durability. And we asked Rosemary and Joel their thoughts on the industry-leading publication from DNV, talking about all the blade problems that exist and what to do about them. And Joel and Rosemary provide some really good perspectives on that. And then our wind farm of the week is the Rattlesnake Road Wind Farm up in Oregon. I'm Alan Hall, president of WeatherGuard Lightning Tech, and I'm here with the vice president of North American Sales for Wind Power Lab, Joel Saxum, and renewables expert, Rosemary Barnes. And this is the Uptime Wind Energy Podcast. Up in Norway, Equinor has put the Trollvind project on hold due to technical, regulatory, and commercial challenges. The project was aimed to address the electrification needs in the oil and gas industry and provide power to the Bergen area. And obviously in Norway, anything offshore is going to be floating. So the problem appears to be that the floating technology that they were going after wasn't fully developed enough for Equinor. And then obviously the project financing, everything got more expensive over the last couple of years, and the project didn't make any sense anymore. So they're not necessarily killing it, but they're just waiting for the technology to develop a little bit more. So I think this is a real interesting case because off the coast of Norway, and this is off the southwest coast of Norway where this farm was supposed to be, it's really tough environment there, right? And because they had to they're trying a unique way of doing floating offshore with the cables, suctioned into the seafloor there. They just felt like they didn't have the technology breakthrough that they needed. And Joel, I think this is going to be pretty common as we get further and further north, right? It's a rough area to put wind turbines in.
I think it's going to be common right now with offshore floating wind, right? Because there's what we've talked about over the last 6 months, year of all this floating wind is there's so many different designs. There's so many different engineering teams working on this problem. We know there's ways to do it. We know there's tension leg platforms and spars, and there's this floating here, and we can moor it this way or we can moor it that way. But then have we really decided, can we just take the same nacelle and tower or nacelle and bearings and blades and throw them on these things? We don't, in my armchair engineering opinion, I say no. But all of this stuff isn't quite sorted out. So you see, we've talked, and so I don't know if it's necessarily talking about, yes, it's rough seas, southwest Norway. The whole Norwegian coast can get pretty bad. But I think it's just floating wind in general. If someone right now says, we're gonna put in a floating wind farm that's gonna be utility scale, I don't think the industry's ready for it. You have California that has the whole floating thing going on, and we've been hearing now, I mean, of course, some of this is regulatory driven, but 2032 before we see anything out there is some of the words that we heard at ACP. So, I mean, that's 9 years down the road. So I don't necessarily think it's environmental conditions. I think it's just floating wind in general is not quite ready for utility scale.
Yeah, and I just got PES Wind magazine came in the mail, And there's an article actually about Norway and offshore wind and how difficult it is. And the article is really good because there's a lot of nuances here. It's not as easy as we're just going to put some wind turbines out in the water. They need to do a bunch of work out there first. And obviously Norway has a lot of experience in oil and gas, but this is a little bit different, right? It's just a little more complicated problem.
Yeah, but I think that like you said, the big markets for floating offshore wind are going to come in the 2030s, and so companies like Equinor are trying to get that lead now. I mean, most of the floating offshore wind farms that are in place already are Equinor ones, so they have built up leading experience, and I guess they felt like this one was moving a bit too fast, but for now, and someone like Norway, it might seem like, oh, this is a really stupid way to put a wind farm in because there's plenty of opportunity for fixed bottom offshore wind in Northern Europe. So why bother going to the expense of developing new technology for floating wind? But the long game is that floating wind isn't going to be competing with fixed bottom wind. It's going to be competing with other ways that countries like, states like California, countries like Japan, places that don't have the possibility to really build a lot of any other kind of renewable energy technology. They're going to be having floating offshore wind, or they're going to be looking at, really expensive solutions like importing liquid hydrogen or, something like that. Or in the case of, Japan, trying to build interconnectors with their neighboring countries who they're maybe not that politically friendly with. So I think it's wrong to consider floating offshore in comparison to fixed bottom offshore or onshore for that matter. Definitely the lucrative opportunities that companies like Equinor want to be the leader for are going to be in places where they don't have other alternatives. And I think once they get through all that and learn from those kind of projects, which will be expensive, there is the scope for floating offshore to come down and eventually be cheaper than fixed bottom. It's it's a possibility. It should be less resource, less materials intensive. There are some advantages for maintenance and that sort of thing. So I still think over in the time frame of a decade or two that it's definitely a promising technology. I think that this particular project will be just a tiny hiccup, and you've got to remember that it comes in the environment of every infrastructure project is having huge problems at the moment with supply chains and that sort of thing. So it isn't surprising that they want to put a pause on this one and focus the wind turbines that they can get, the steel that they can get, onto projects that they know are going to make money now.
Yeah, and in the grand scheme of things, the Norwegian electrical grid is 90+% renewable already, right? It's mostly all hydro. So it's not like they're hurting for energy or hurting for renewable energy. Most of this stuff would probably be exported. So at this point in time, maybe it makes sense financially, like they've decided to pump the brakes.
Equinor has such a vast amount of experience in offshore wind that they can assess these things probably better than any company on the planet at the moment. And I think they're making the right decision for now, for sure. Or over in the UK, the National Robotarium and Fugro are collaborating on the development of an electric remotely operated vehicles for maintenance and repair tasks on offshore wind turbines. So, Joel, this is right in your wheelhouse. The partnership is part of a £1.4 million underwater intervention for offshore renewable energies called the UNITE project. So they always have to have an acronym, right? Always an acronym. United States, UK, same thing. Got to have an acronym. The UNITE aims to enhance health and safety in the offshore wind industry by reducing the need for potentially hazardous maintenance missions conducted by crewed support vessels. The ROVs, as they're called, will address various sector challenges, including reducing carbon emissions, improving turbine productivity, and making maintenance and repair exercises more cost-effective and efficient. So, Joel, what they're thinking is a lot of these offshore wind inspections and surveys can be done remotely with a battery-powered vessel. Is that seem plausible in the long term or even the short term?
Short term, man. So these projects have been going on for quite a while. This isn't the first one of its type. Some of the first projects were, all right, let's go out with our normal vessel, crewed vessel, and we'll put a ROV in the water. And now we're going to make it a little bit more efficient by giving it some kind of machine vision or something, right? So now it can it can do an inspection of the monopile, say subsea, by following it itself. And instead of having a pilot fly it, you remove that pilot cost, but then you're also more efficient in getting it done. So that was step number one. That's cool, right? So now we've got something that can autonomously inspect a monopile or a cable route or something like that from the vessel. So at the same time, those developers were creating autonomous surface vessels, which like X-Ocean has one, Drix, Teledyne, the Gavia system, Kongsberg has some. Everybody makes them now. They're surface vessels that are basically robotic, and you can launch them from another vessel or from shore, and they can go out and do route surveys or other things of that sort. So now you've got hey, we can do this ROV here. Now let's take that ROV, let's cut the umbilical and let that thing be an autonomous underwater vehicle to like survey a cable route by itself. So now you take that same machine vision smart stuff, put it in the water, and it can follow a cable route and inspect a cable route by itself without having the vessel. Super cool. Now you've gotten a couple of different things here. Now you take that AUV and the ASV, and then you put those together. So now you can go quayside, you can be onshore in the port, and you can launch a vessel that cruises out by itself and then releases an autonomous underwater vehicle. It becomes basically the primary up top. The secondary vehicle goes down, does its inspections, comes back, mates back to that primary vehicle, and then they go back to shore. And now you can do it all on electric power or hydrogen power. That's happening as well.
How many of these vehicles could they possibly need? Now, the UK is planning to have like 11,000 offshore wind turbines in the near future. And obviously, they're going to keep putting them out there until they don't no more need for electricity, I guess. So you're talking about maybe 15, 20,000 wind turbines offshore. How many of these vessels would they need to go do this work? 5, 10, 100,000?
Probably 100. I would say you're if you look into operations and maintenance for offshore wind farms, there's a lot more going on than you think. It's not just changing oil and looking at the blades every once in a while. There's a lot of things that happen subsea and even topside. So there's been a few programs. I know Perceptual Robotics was a part of a program taking in one of those ASVs out with the drone on top of it, launching it quayside from shore, autonomously driving it out to the wind farm, and then taking a drone off from the deck and inspecting the blades and coming back. So now imagine if you had that vessel with a drone on it and with an AUV, so you can go out to a turbine, drop the AUV, do the subsea inspection, take the drone off, do the topside inspection, come back, boom, boom, land them both, move on to the next one. You're removing the ROI on that is amazing because you're removing a $50,000 to $100,000 a day SOV with 60 people on it.
Are there regulatory restrictions on that kind of operation where you have a remotely controlled vessel?
Yeah, absolutely. I mean, you have the drone regulations, but then you have the same kind of things for, that vessel needs to be able to abide by all maritime laws. So it has to. I mean, there's autonomous vessels. Ocean Infinity has created the Armada fleet. They're 73 meters long apiece, and they're ghost ships. There's nothing else. You don't need anybody on them technically to drive them or to operate them. So this stuff seems like science fiction, right? It's not. It's going on every day right now.
Hey, Uptime listeners. We know how difficult it is to keep track of the wind industry. That's why we read PES Wind magazine. PES Wind doesn't summarize the news. It digs into the tough issues. And PES Wind is written by the experts, so you can get the in-depth info you need. Check out the wind industry's leading trade publication, PES Wind, at peswind.com. Well, over the weekend, I was at an urgent care facility, and I had a lot of free time on my hands. So what did I do? I started looking up Wind Power Lab's LinkedIn page and reading all the things that were posted. And one of them was the new DMV report on the challenges of wind turbine blade durability. I thought, well, I got a couple hours to kill. Let's go through this thing. And it was a remarkably good document summarizing all the blade issues I think all of us have been talking about. And to see it in a sort of condensed form out of DNV, which is obviously everybody respects, is a good start, right? So let me summarize what they see are trends in wind turbine blades. One, higher uncertainty in blade maintenance costs for new blade models. True. Significant blade problems affecting the industry, including top-tier turbine and blade manufacturers requiring large, time-consuming inspection campaigns. Boy, don't we know about those. Significant numbers of turbine collapses due to blade failure. Yep. An increase in severe lightning damage, particularly on blades with carbon components. And yes, we all have experience with that. Structural blade damage initiating from relatively minor features that would not have been expected to have propagated in the past, for example, at conventional details such as core ramps, Rosemary. And then higher incidence of severe leading edge erosion early in operating life. I think we all here have seen all of these things. That Rosemary has been probably a lot closer than Joel and I, but does that make sense, Rosemary, that all these are the sort of the highlights for blade problems at the moment?
Yeah, it's interesting because I haven't been working in this part of the industry for more than a few years, right? So I haven't seen a trend. I've been surprised. My background was working for wind turbine manufacturer, and before that, it was in academia, designing, the research and new methods of design. And so I've seen the broad trends in the industry. But then when I came into working on defects and helping manufacturers, resolve issues with potentially serial defects, I've been surprised that there were so many, that they were so common, but I didn't get that snapshot of, I've only got a snapshot. I haven't got that experience from 10 years ago. How many blade serial defects did we see in wind farms? I've only seen what it's like now. So this is really interesting to see this report and have them be able to provide that trend over time and say, yeah, okay, this the amount that we're seeing now, it is an unusually large number of failures compared to what we saw in the past. And it makes sense. It fits in with what I know. Like I've noticed with Lightning, I was working a lot with the Lightning team when I was working for a manufacturer. And so I did see the change there that, the previous Lightning systems were a lot more simple and they worked pretty well. They did what everyone expected them to do. And then with the newer systems, everyone kind of realized that, blades are really changing a lot. They're getting longer, fast, they're getting new materials in them, and things are a bit different now that blades are so long. And with these new materials, then it means that a lot of the technologies are complicated and have changed quickly. I definitely felt that in the period that I was working for the manufacturer, that, the start of the time when I was there, I think I started in 2016 at that company, things moved at a nice, safe pace that engineers could feel okay with. Things are changing, but we're all confident in it. And then a couple of years into that role, all of a sudden it's like, we've got to move fast. We've got to put out a longer blade. We've got to, if you want to keep up in the market, we've got to put out bigger and bigger turbines. We've got to use carbon fiber. We've got to, all these other technologies, protrusions, and there'd be a dozen of them that all came in within a few years. And then a few years after that, you start seeing, okay, a lot of these really fast projects have issues, which, you would definitely expect that. You can't change things and have it, do exactly what you expected every time. So it does make sense to me that there's a lot of failures are resulting now from that. And it's good to see it all put together in one place.
So you don't think it's technical challenges as much as the speed at which the industry had to move?
Yeah, the speed that the industry had to move highlighted the technical challenges, because in the past, you would have had, the company would have been working on one or two new technologies like this, and they probably would have taken a lot longer to, feel good about putting it out. But, there's been some really big changes now that have happened in just a few years. So, you don't have time anymore to say, okay, this is a new technology. We'll test it in the lab first. Then we're going to make a test blade and see how that works. Then we're going to put it up on a test wind turbine and wait a few years to see how that performed. And then we're going to roll it out gradually and then keep on learning from the experience and bringing it back in. Because when you do it like that, it takes, first of all, that process takes many years. But secondly, if you've just got a couple of test turbines, that's not enough instances to start to see, statistical rates of failure. And that's what you get when you've got, even if you did go through that whole process I said, and you've got, like one test turbine at the end of your 5-year, technology campaign, one test turbine that's been out there for 2 years. And that would be like a super conservative, slow way of developing a new technology. Then, so that's got 3 blades on it. And then, okay, now we're doing serial production, and you don't, do a little bit of serial production. If you want to, get the benefits of that whole process and how, everything is designed to get costs down, that means that you're, putting a blade out of the factory every single day. And, every other factory that's making components for the wind turbine needs to be operating maximum on the one thing over and over and over again to make that cheap. So you go from one test turbine up to at least hundreds and more likely thousands of wind turbines out there with this same design. And then failures don't happen immediately. They happen, after a year, 2 years, 3 years. Usually in that first few years period is when you start to see the bulk of the problems. But then there's thousands of turbines out there. And so it's a delayed response. So, of course, the manufacturers are then going to go back and, make the changes that they need. And that's totally normal, iterative design process. However, there are hundreds of wind farm owners that are distraught over the fact that they've got these big failures. And, in the case of a wind turbine blade or any other component, big component like that, it's no trivial matter to replace these. Getting a crane out there to a site after it's already been fully commissioned and, all the cranes have gone. Getting a crane back there can take a long time. I don't know what it's like in every country, but in Australia, there's not that many cranes around that are, big enough to install these modern 100-meter plus tall wind turbine towers and all the parts on them. And then, other complications have the factories, the turbine factories, have they moved on from that particular design and now they're, cranking out another one. It might mean that you have to get, for example, in the case of a blade, you have to get a blade out of the yard and a mold out of the yard and bring it back into the factory and then set it back up just to make, a few blades to replace it. It can take a year, to replace a blade. And I don't know, I think probably a lot of wind farm operators listen to this podcast. I don't think that any of them would like the thought of they've got a turbine sitting by idle now for a year while they wait for a new blade for, a manufacturer defect that everyone accepts is their fault, but doesn't make you feel any better about every day that goes past with your turbine shut down. So, it's a natural consequence of moving so fast. We need the technology development to happen, but it kind of I don't know, it didn't happen gradually. You might have expected, we've had utility scale wind turbines since the 90s or so, say. Why is it that in, the 2010s, we had this sudden acceleration in technology development that's causing headaches now? It might have been nicer if we'd been able to smooth it out over that whole period, but it's not the way it's worked out. And we'll definitely reap the benefits in 2030. I'm sure all the turbines will have moved past this crunch, and hopefully the pace of change will slow down a little bit. I mean, it should. But for now, it can feel like things are out of control. And, I bet that the warranty departments of the wind turbine manufacturers are really crazy busy at the moment based on the amount of work that I'm seeing.
Well, that's where D&V comes in here, because they have picked up on all those things, Rosemary, and I think they're trying to plug the gaps with some of the recommendations. So I want you, Joel, and you to hear some of these and provide feedback on them, because Rosemary, from the manufacturer's perspective, Joel from the aftermarket and seeing these blades in service, I think D&V has done a pretty good job of figuring out ways to eliminate some of these problems. First, conduct detailed blade diligence prior to manufacture new blades for a project, which would ideally include design for manufacturer reviews. Such reviews evaluate the intersection between blade design, manufacturing, and quality processes to identify previously uncovered risks. I think that's first of all, a good thing. We do it in aerospace all the time. I haven't seen it much in wind, but this makes sense to me.
Oh, that's a great shameless plug for DNV's business development department, right? Because that's what they do. They're the ones who certify them.
But they have certified these blades also. I mean, let's be clear. I mean, aren't they also, insulting their own process?
I should say we should conduct more detailed blade due diligence before we let these guys go. No, I think they do. Yes, all of them are certified, of course, but I think that the tough thing here is unless it's in the certification process, GE, Siemens, Vestas, they're not going to open up their playbook to give to anybody. They're not going to give it to Wind Power Lab. They're not going to give it to an asset owner. They're not going to give it to an insurer. They're not going to do it. So unless it's the body that is certifying the process, those are the only people outside of the OEM that get to see these designs.
I think that DNV might be being a little bit naive here because, I mean, I don't know about you, Joel. You work on root cause analysis as well, right? Yeah, the ones that I've worked on, the root cause analysis that I've worked on, it's not like you get the root cause and you're like, oh, well, duh, you should have known not to do that. It's always a new technology and it has caused a new failure mode that no one had ever seen before. It's not something you would check off if you went through and, witness the manufacturing of a blade and it would be obvious to an outside observer that this is going to cause bad quality. It's new stuff where you don't know yet how it breaks. And I mean, I often say that, I've got like 20 years engineering experience now, and the main point of that is that I know how things break, right? That's any of us that have been in the field for a long time. You can look at something, you can say, okay, this is going to break here, 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 and here. So we'll test for that. There are dozens of great engineers with decades of experience on any one of these blade projects that have looked at it and said, this is where it's going to break, here, here, and here. And they have, listed out the things that they think could go wrong. And during these really fast periods of development, sure, they're not going to get to every single one of those risks that they've identified. And it causes a lot of angst in the, in the canteen. The engineers are talking together, stressing about a risk that they've foreseen that they can't test. But that's not always the thing that ends up going wrong. And it's quite normal in an engineering design process that, you prioritize your risk. You do the ones that you think are likely to happen, and you do the things that would have really bad consequences if they happened.
Here's one thought as well. In the engineering world, composites specifically are very hard to model. And the reason being is because from piece to piece, you're using balsa wood, right? That's a natural phenomenon. So like, it's not like you have this X grade steel and you're going steel to steel. Those things are easier to model. It's easier to model the aluminum frame of a car than it is to and see where it will fail and what will happen under loads and these things than it is to have a composite structure, because a composite structure by design is inherently this art meets science. Not everything is perfect. So those are tough as well, right? And what we see, I know from the RCA standpoint, Rosemary, like you're saying, is you can do all the due diligence you want on the design, yes, but you have design errors. These are things coming out of the factory, right? You have design errors, and then you have manufacturing errors. Two completely separate things. Because we see a lot in the RCA world where it may have been designed just fine, but all of a sudden, like, the shear web isn't glued properly, or you have a kissing bond instead of a good mechanical and chemical bond in a joint or something of that type. So some of those things, though, when you see them, right? Like we've seen fleets of blades that have in the leading edge where there's an overlap in the leading edge where they sandwich together, they bite together, and then they put basically what would be a piece, the glue that sticks them together and the tape on the backside, as for bad terms, but those things aren't properly mated, right? So that technically, when you see a bunch of those, that looks like a manufacturing error, but it's actually a design error because it's the design of how you manufacture them isn't proper. So some of those things, how long and how long do you get to review?
I think that you're definitely right, but I wouldn't agree that a design error and a manufacturing error are completely separate, because if you work at a manufacturer, as a designer, then your job is to design for manufacture. So it's very easy to, make a recommendation. Oh, you should be designing for manufacture. Of course they are. That's what they have, they're decades of experience, these manufacturing companies. And all of their learning has been about, this is the way we designed it. This is how it's actually built. So they either change the design to avoid that error, or they know the strength of the real as-built material. They're not just going off, little perfectly made samples that they've tested in a lab and then making their design off that, and then crying when the real manufactured wind turbine blade isn't strong enough. They maybe did that, back in 1980, and learned from it. And there's a big, when you look at old wind turbines and look at a lifetime extension, one of the big reasons why you're able to extend the life often of a wind turbine blade that should have already used up its life is that we know so much more now about the actual strength of these components as built. So you can say, okay, we used to use a safety factor of, I don't know, five times, and now we know that it's actually okay to use one of 3.5 times, or whatever the factor may be in the specific example. So yeah, I definitely you're right, and I mean I'm certainly never looking at root cause analysis where they find the root cause was that the design was just wrong. It's always that the manufacturing did not allow the finished blade to have the design intent. And so, yeah, you're definitely right that that's the issue. And I guess DNV is right that that's the issue. But DNV is wrong to say the solution is designed for manufacture when that is most definitely what is already happening. It's a bit it's a bit easy, right? Oh, you should think about how these products look when they're actually manufactured. They're saying that to a manufacturer, the bulk of the employees in any of these companies are manufacturing employees. They're not, design engineers are, at LM Wind Power is a few hundred design engineers. And then there's, 10,000 manufacturing employees. So, it's, come on, they do think about manufacturing.
Let me go through a couple more bullet points here from DNV, because I think this is important. And they're going to touch on some of the things, Rosemary, you mentioned, and Joel, you mentioned them too. Reference DNV's turbine review reports, which include risk statements and technical evaluation of specific blade models based on DNV's experience. So sort of like looking back and then applying what you learned from the previous blades onto new blades. Makes sense. Evaluate blade manufacturing facilities, capabilities, and processes. This includes review of factory conditions, process capabilities, in-process blade fabrication quality system effectiveness, and the finished product. So again, if blades are made in different factories around the world, are they out producing the same level of quality? Are they all doing the same thing? That's a decent approach. Monitor blade production. Okay, this is the interesting one. Monitor blade production, which may include witnessing manufacture of and evaluating the quality of blades for a given wind project. This process seeks to reinforce good quality, prevent or capture flaws, and possibly influence blade manufacturers to modify or improve processes that result in quality lapses and escapes. So what they're saying is putting another set of eyes that's not getting paid by the manufacturer into the facility to monitor for quality. A separate oversight.
So we speak about that with a lot of clients at Wind Power Lab. Right now we're doing a large project for an operator in the EU where they're getting some blades made, and they had their first few of the blades delivered to site. It's a phased out site. And when they got them on site, they went to go hang them, and they had issues already. So they're like, hey, we need you guys to look at this thing. So we've done it in multiple manufacturing facilities, basically audits of the process. And then I think the next bullet here we'll talk about, probably it goes along the same thing, is inspecting them as they roll off the line, because you can repair them at the factory much better than you can repair them in the field. And then if you're not following your process, because that's the big thing, right? So when we do these site visits and these QA/QC things, they hand us their processes and we go through the processes and then look at the end product. And if the end product doesn't match what the processes say, then they've got to go back and fix it. And sometimes there's just stupid stuff, right? Like handling mistakes. There's a crack in the gel coat because they grabbed it in the wrong spot or something like that. Stuff happens all the time. But yeah, you'd be actually really surprised to see that these blades coming directly off of the manufacturing floor are already full of defects.
I think insurance companies are going to get to what the next DMV bullet point is, which is inspect blades and assess for inspection results. And DMV goes on to say this may include detailed internal and external inspections of new blades before or after installation on the turbine, as well as at the end of warranty and during operations phases of the wind project. So, Joel, you've hit right on it. The insurance industry is going to force this. This is not going to be a DMV-driven thing as much as the cost of insurance.
It's interesting though, because most of these suggestions are already things that are, well known in the industry and are being done. I've seen a lot of cases where, there has been all the proper inspection, quality inspection throughout the process, but because it's a new a new design feature, say either a new material or a new manufacturing process or something like that, it turns out that the inspection process actually wasn't suitable for it, but they didn't realize until they started seeing failures and did a root cause analysis. So I've seen a few of those where it's like, we 3D scanned all this exact feature. I have the images that show there's no flaws here, and yet, a year of operation in the field, we've got cracks forming. What on earth is going on? And then they realize, oh, okay, we thought that this inspection process would be suitable, but it turned out not to be. And I think the underlying thing for all of this is all this stuff is well known. It's all been doing to a certain extent. You could do it more, and that's easy to say, just do more, take more care, don't make these mistakes. And that, if you said something like that, then you would fit in very well in the engineering department in any of these manufacturing companies. The engineers really want to be very cautious and make sure the product that they're designing is going to be good. But there's this commercial pressure of everybody else is making bigger wind turbines. Everybody else has these new features. Company X has carbon fiber blades now. Company Y is using protrusion. Company Z has a 150-meter long blade. And so it's not possible for a company to say, no, we're going to go safe, and we're only going to make what we know 100% is not going to fail, because they're not going to have any sales. And so maybe in 5-10 years time, their competitors are going to go bankrupt from all of the warranty claims. But they will have gone bankrupt before that because they had no sales for a few years. So that's the real tension, that, stuff like this can't actually solve that. How do you solve those sorts of problems? To me, I think that it's necessary to periodically go through phases where you have a lot of failures in the field and fix them and learn from it. Then you've got the technology and you've got the robustness in a few years. But the period that we're in now, it's very difficult, and for the greater good, that makes sense. But for any individual wind farm operator, they're still stuck with assets that aren't performing as they should be. And it's a lot of work for them to get what they deserve. They deserve to have fully functioning wind turbines for the amount of money that they paid. It's not on them to wear the cost of the experimentation of the manufacturer. So yeah, anyway, lucky that there's people like Joel and me that can help them get the outcome that they need on each of those projects.
A lot of this paper that we read here you're reading down the menu of services that we offer at Wind Power Lab to protect asset owners, right? Monitor blade production, do the inspections, instrument them when you can, monitor them from the lightning, make sure that they're good quality coming out of the factory. Like, these are things that you would think are no-brainers. And Rosemary, you do make a point where, like, yeah, they're stating things that are known in the industry, but it's surprising how many operators don't actually do this, right? So what the term that was used in oil and gas that I take over here as well is having a bird dog in the field. It's the same thing that's used on offshore vessels, whatever. But the bird dog is the client rep. That's that person that is an independent third party hired by the client to come and say, or an asset owner to go and look at the turbine blades. And that person becomes their eyes and ears to make sure that they buy a good quality product. And that person is a seasoned engineer, knows what they're talking about, knows what they're looking at. And it's amazing how many things that you can pick up at the early stages that just aren't seen.
All right, the last two things from DNV are implement a robust blade management program for your new or operating wind projects, including proactive inspections and quality control for field repairs. Rosemary and Pardelote and Joel at Wind Power Lab. Sound familiar?
Standard stuff.
Standard stuff, right. The last one, which affects my little business, is analyze and use data from various types of sensors, including turbine-based lightning sensors, load sensors, etc., to monitor blade durability and lightning activity. So I think what we're saying is you need to be monitoring and inspecting your stuff. It's to keep it that simple. Look at what you own and make sure it's working right, and put some sensors on it so it simplifies your job.
Yeah, know what's going on in the field, right? Especially when you have, and that's what I kind of go back to before about people not knowing, is that what's happening a lot in the world now is it's not so many, not as many people that are big asset owner operators. So there's a difference between an asset owner and an asset owner operator. Right, your big time players, your NextEras, your RWEs, your EDFs, like here in the States, they've got blade engineering teams. They're looking into CMS systems. They have robust inspection plans. They're monitoring things. They're looking at lightning data. They're doing these other stuff. But there's a lot of asset owners out there that are basically financial companies. Right? They don't have engineers on staff. They don't have people on site. They buy the turbines. They develop the site, or buy the site already developed. And then they have an FSA where the OEM takes over and watches after the thing for them. So they just don't know these things, but then they end up getting caught, end of warranty. All of a sudden they got all these damages to take care of, or they get caught having to pay to repair lightning damages because it was a part of their contract but they didn't monitor for lightning damage and these different things. So there's a lot of people out there that are flying blind. And so they say great things. A lot of people are doing this stuff, and it's things but if you're not a specific engineer,
it's complicated.
Yeah, it's better to read a document like this, or listen to experts like Rosemary, or the company I work for, Wind Power Lab, or when dealing with Lightning, Allen, or any of these CMS companies or other experts in the field. Learn the lessons from the experts instead of taking the black eyes and the lumps yourself.
Joel, over the weekend, because I was sitting there in that urgent care, I decided to put out a little summary of what I thought on the lightning aspects, because the DMV article goes on to say for lightning things they're going to update the IEC spec for lightning, and they're going to suggest, I don't want to say requires because it's not a requirement, but it will be because insurance companies are involved, to put some lightning monitors on your turbines so you can see the current waveform, all the lightning pulses and that kind of thing. Been in the lightning world a long time. I'm not sure what you're going to do with that data. It's just like too much info, right? And we already have that info. It's too complicated for operators to sift through. Like, what are you going to do with it?
That's why we created the Lassie system at Wind Power Lab, right?
It's got to be simpler.
We will do it in the background for you, and then just give you notifications of, here, this is what you need to do. Here's what you need to do to your turbine. Not necessarily here's all the engineering data analysis, data science that you have to do. Like, that's... people don't have time for that.
I think the Lassie system makes a lot of sense. In places where we're seeing there's a lot of lightning strikes and you need high levels of accuracy, I think putting on a lightning sensor makes a lot of sense. The one from Ping is probably the least expensive one on the market at the moment, because it tells you you've had a lightning strike, an actual lightning strike, and then it can determine if there's damage to the blade and send out an alert. So that makes sense on the cost side of it for sure. And Joel, you're right. If you got a farm, it's not a lot of turbines, you're not in a strong lightning area, for sure. And the Lassie system makes total sense, even on large wind farms in the States, because at least gives you a sense of what the hell's going on. If you don't have anything on your blades right now, your turbine now, that at least gives you some oversight to it, right?
Monitor them somehow.
Modern, but it doesn't have to be expensive or complicated, and that's what I want everybody to hear is like, don't make it too complicated. And after reading this, I've been in 3 separate industries in my career. Start off in spacecraft, which you make 1 or 2 spacecraft maybe a year. Moved over to aerospace, where you're making dozens, maybe a couple hundred of aircraft a year, and then being around this wind turbine business a little bit, where you're making thousands of something a year, right? Because of the quantity, it changes the way that the manufacturing and the engineering have to happen. And as Rosemary was pointing out, things have to go faster, right? When you're producing thousands of things, you just got to be faster. What I have noticed in all 3 industries is just the level of quality changes dramatically as you get in, and the organizations change. But to a company, the ones that I've seen work are ones where manufacturing and engineering are working together. They're not two separate siloed organizations. The engineers are not free from criticism from manufacturing, and the manufacturing is not free from criticism from the engineers. They need to be kind of coupled together, and the management over top of those companies needs to force that interaction. So it's not, I design it and then I don't worry about it. No. You're designing it and you're living it, what's happening on the floor. That's where you seem to get the best kind of product coming out. And engineers don't like getting your hands dirty. Let's just face it. Like, a lot of engineers like to sit up there and type on the computer. It's nice and have your coffee and your thing, and it's sure. And a lot of manufacturing doesn't like talking to engineering because they're upstairs in their air-conditioned offices. It's the nature of the business.
You're exactly right. And one of the issues that we have within the wind turbine business is logistics, right? Because these blades are getting so damn big that if you're going to build a wind farm in India, there's factories over there, right? They're not getting designed there. They're getting designed in Germany. They're getting designed in Denmark or wherever. And there's manufacturing all over the place. So those engineers aren't in there embedded in the factory.
It makes it hard. As soon as you open the second factory, and Boeing went through this, right? So Boeing went through this. I'll use Boeing as an example because they had problems. When they had all the factories up in Washington where all the engineers were, then they opened a factory to make the 787 down in South Carolina. And sure enough, right, they started having problems because of the lack of oversight. I think it's that the engineer couldn't walk down on the coffee break and kick the tires on an airplane. They were now 2,000 miles away from it. Those interactions create problems, and Boeing's been teething through those. And I think it's a similar thing that we see in wind, where engineers and the manufacturing are thousands of miles apart.
Ping Monitor is a continuous blade monitoring system which allows wind farm operators to stay ahead of maintenance. Wind techs can often hear damaged blades from the ground, but they can't continuously monitor all the turbines. They also can't calculate how bad the damage is or how fast it's propagating based on sound, but Ping can. Ping's acoustic system is being used on over 600 turbines worldwide. It allows operators to discover damage before it gets expensive and prioritize maintenance needs across their fleet, and it pays for itself the first time it identifies serious damage or saves you from doing an unnecessary visual inspection. Stop flying blind out there. Get Ping's ears on your turbines. Learn more at pingmonitor.co.
Joel, our wind farm of the week is the Rattlesnake Road wind farm up in Oregon. So EDP Renewables North America is actually celebrating the 15th anniversary of the Rattlesnake Road wind farm in Arlington, Oregon. And Arlington is like in the center of the state, right along the border with Washington. Nice area, by the way. The 103 megawatt project in Gilliam County produces enough energy to power the equivalent of 29,000 Oregon homes annually. Rattlesnake Road represents an estimated capital investment of $226 million and contributes to the local economy in a variety of different ways. During construction, the project created more than 100 full-time equivalent jobs, and it currently employs 17 permanent positions to operate and maintain the project. Yikes. Rattlesnake Road has also contributed more than $23 million worth of spending within the 50-mile radius as everybody goes out and buys gas and has sandwiches and
snacks at lunch, coffee. Yeah, gotta have that.
Yeah, all the good stuff. And in addition, the wind farm has dispersed more than $8 million to landowners through land lease payments and paid more than $13 million to local governments, area schools, etc., in form of payments and taxes and those kind of good things. So it's a huge money dump in the sort of middle of Oregon. That's a great thing, right? And it's a 15-year project. So Joel, they're going to be getting ready for a repower probably in the next year or two.
Absolutely. I want to stop you there for a second, Alan, and I like that we're going through some of these stats here, because in the background for our listeners here, we've been talking about some of the public relations and things that we feel maybe the wind industry doesn't do that well. And sharing this year, $8 million to landowner lease payments in the area, $13 million to local governments with benefits for schools and emergency services, infrastructure. I'm sure they helped with some roads and things around there. $23 million just spent in the community. This is one wind farm. In the United States, there's hundreds of wind farms. There's 72,000 and change wind turbines around the country. So this is just a small snippet of what the wind industry gives back to the world as well.
Yeah, I think this is great. So congratulations to Rattlesnake Road Wind Farm. You are our wind farm of the week. Joel, we were on Twitter and we're getting a pretty good response from it already. So people can check out Weatherguard Lightning Tech's Twitter page and you can watch full episodes of the Uptime podcast. But Joel, you're on Twitter also.
Yeah, so at Joel Saxum is my handle on Twitter, but what I'm trying to focus on is the same things we do on the Uptime Wind Energy podcast. So you can see that's kind of what I've got Twitter set up for, but it is to share some of the innovation, technology, permitting things, government activities within wind, what the OEMs are doing and all the above, all over the world. So the same thing we're doing with the podcast, we're sharing as well on Twitter. Come and check it out.
Yeah, Rosemary's on Twitter also, so you can check out Rosemary. Rosemary's Twitter handle is @ENG with Rosie. That's going to do it for this week's Uptime Wind Energy podcast. Thanks for listening. Please give us a 5-star rating on your podcast platform and subscribe in the show notes below to Uptime Tech News, our weekly newsletter. And check out Rosemary's YouTube channel, Engineering with Rosie. And we'll see you here next week on the Uptime Wind Energy podcast.